12, 3, chi-squareds. So let's preface this. You guys are lucky in the fact of yesterday was my trial run through on this lesson. I did a horrible job yesterday. Hopefully by the third time today, you all are the third time, we got it down a little bit better. So let me explain to you quickly about 12.3. Okay. Linear regression. Inference for slopes. Bivariate data. 90% of what I talk about today is from chapter 3. It's more of a review of chapter 3 than it is new stuff. Okay? Basically, we're combining all the stuff from chapter 3 and chapters 10 and 11. 10 and 11 was inference for means, confidence intervals, hypotheses, testing for means. Okay? So let me again preface this section, right? I got all 9 units over here from AP Stats, all 9 units. I know we have 12 chapters. Shh, guys, we have 12 chapters, right? Some of our chapters got combined. This is bivariate data, unit 2. That was our chapter 3. Okay. It says the AP exam will cover anywhere from 5 to 7%. So 5 to 7% of the AP exam comes from chapter 2. This is 12.3 all by itself. This is 12.1 and 2. This is chapters 10 and 11, and this is chapters 8 and 9. Y'all kind of okay with all that? This says 2 to 5%. So there's very little, if any, on this. However, to do this, you got to know this. So this is 5 to 7. This is 2 to 5. So 5 to 7 and 2 to 5 is somewhere between 7 and 12. So now we're kind of getting up there, decent amount of questions. If you don't know any of it, is it going to kill you? No. If you know all of it, is it going to help you? Absolutely. Fair enough with all that, right? So this is where we're at on that. To give you heads up also, next year they're changing all those. There's not 9 units next year. And one of the units they're getting rid of is what I'm getting ready to tell you about today. So I got 2 thoughts. Either they're going to put more of it on this test because there's not any more, or they're going to phase it out this year because it's not in next year's. Y'all kind of follow what I'm saying? So I'm going to go ahead and teach it like there's going to be some questions on it. I believe there's going to be some questions. I do not think it's going to be a free response question. I think it's going to be multiple choice questions. Okay? You'll see my notes are not the greatest. There are many years I've never taught this lesson. Many years because because it's so small, I just cut it out. And I did a disservice to them. So just kind of keep all that in mind as we're going through this, okay? I did a horrible job yesterday, so I'm filming it today, hopefully to fix it from yesterday's class, okay? Most of what we do today is review from bivariate data, linear regression, y hat is equal to a plus bx. You got a slope and you got a y-intercept and you got r and you got r squared and you got s, the standard deviation of the residuals. We got residuals. Holy cow, right? I know it's been a long, long time ago, but a lot of that's going to be in today's lesson. Okay, I think that's the most beneficial for this is the review of that chapter. Okay, also we still got t's from chapters 10 and 11. So that's going to come into play. So it's going to be a review of that. We're going to kind of put all that stuff together. Y'all good? Inference for linear regression, right? So just kind of watch and learn. Just kind of watch first. Don't try to take anything down. And yeah, this is kind of like the understanding part of it. We got Old Faithful, geyser, right? All population, 263 eruptions in a single month. So they took 1 month and they got every single eruption for the entire month. So we got a population of 1 month. Y'all fair enough? Click. There's a scatter plot of it. This is the duration, how long, and the interval between it and the next one. So 50 minutes between them, and it lasted this long. You're kind of okay with all that stuff. We got a big cluster right here. We got a big cluster right here, and we got a couple of these points in between it. It looks like a fairly strong, moderate, positive, linear association. Oh my gosh, that's R. R squared is the percent of variability in Y. Yay, good enough with all that soaking that up. We know that we have Y hat is equal to A plus BX. A is my y-intercept, B is my slope. We use hats for Y because we're predicting the value of Y from an X. Y'all good, yay? Okay, so this is a slight little bit. That's all we did in chapter 2, 3. Chapter 3 is all we did here because everything was samples. Everything was samples. We just didn't talk about samples and populations then. This line here is actually, whoops, it's nothing without a pencil. Dadgummit. Here I am thinking I did all this stuff and got ready, and I forgot to turn that on. Bear with me. This is actually Y hat is equal to alpha plus beta X because it's the population, right? This alpha is different. It's not the significance level. This is not 0.05. Okay, this is different alpha. This is the y-intercept alpha. I know that could get first confusing. Anytime we have Greek letters, those are your populations. Mu is a Greek letter. Rho is a Greek letter. Greek letters are populations. Alpha is the population y-intercept, and beta is the population slope. Just kind of soak that up. That's not, yeah. This, click, 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 click. This is a sample of data from those geysers. 1, 2, I don't know how many there are. It's got Y hat is equal to 44 plus 10x. The green is the sample regression line. The blue is the population regression line. Just kind of soak that up. We know what samples are going to vary from sample to sample. Not only are they going to vary from sample to sample, they're also going to vary from the population. I did another one. I got another green line that doesn't match the blue line, and it doesn't match this green line. I got another one. And if I got another one and got another one and got another one and got another one and got another one, eventually I'm going to get the sampling distribution of lines. Yay? Which will look something like this. This is the population slope. We don't care about the y-intercept, right? Y-intercept very seldom, if ever, tell us about anything because that's often extrapolated. So this is the population, and these are all my slopes, right? They're close to it, and as we get further away, it's less likely to happen, yada, 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 yada. Again, just stuff just to kind of make us look ahas. Nothing about this is going to be tested on. Click. You don't care. Click. You don't care. Click. Conditions. Is that my computer? It's on its last leg, I'm telling you. Is that the fan, or is it making a noise? Yeah, it's on its last leg. It probably didn't help the other day that the fan was making all kinds of noise, and I just kicked the pootie out of it. And the fan quit making a noise. I don't know if it's a good thing or bad thing. Who cares? Conditions. I really believe this is for homework only. I'm not going to ask it on my test. I don't think it's going to be on your AP test. But I want to go over it because then I can just say, well, at least I went over it. Okay, these conditions are different than all other conditions. They're different than all other conditions. Well, the first two are not. You still have to have randomness, and you still have to have the 10%. Linear is the first condition. The data needs to look linear. The relationship needs to look linear. If it doesn't look linear, it doesn't make sense to do a linear inference. Oh, that would make sense, right? If it doesn't look linear, there's no way I'm going to do linear inferences. I'm not going to do a confidence interval, and I'm not going to do any hypotheses testing if the data doesn't even look linear. This one's okay to do inferences for. That one is not. Y'all okay with that? Again, you won't have to do this, but it's just something that just should be common sensey. I just want to make sure you know that. Okay, so the first thing is, this is a good one and that's a bad one. We want it to look linear, okay? We want it to be independent. This is the 10% rule. We want our sample to be less than 10% of the population. That's what independence is. That's the 10% rule. 10% checks my independence. Each sample is independent of the previous one if it's less than 10% of the population. Because even if it's dependent, it's so small it might as well be independent. So that's the second one, okay? Linear, independent, normal. We normally call this one large counts, but they're not going to use large counts for this one. And what we mean by normality is, we want a box plot or a bar graph or some type of a picture of the residuals. We want the residuals to look approximately normal or non-skewed with non-outliers. We want the residuals to look non-skewed, non-outliers. Again, homework questions, not a test question. Maybe AP. But if it is, it's a very, very small amount. Okay? Equal standard deviations for the residuals. Equal standard deviations for the residuals. So y'all remember, I hope at some point, you'll aha moment, right? We got a residual plot. That's the plot of the residuals. We want the residual plot to be scattered. This is okay. That one's okay, but that one's not okay to do inferences for. That one's okay to say it's linear. That one's not okay to say I can do inferences because the variability is not the same. It's tight here and then it becomes wider. This variability is about the same. We want equal standard deviations of the residuals. If you want to say equal variability for the residuals. Okay? Again, homework, not my test. Equal variability. Bad one, good one. And then, of course, random. Random. We need a random sample. We need a random sample. Those are the conditions for linear regression. Different than all the others. Sort of. We still got random, we still got 10%, and the reason why I put them in this order is because that's a L, and this is an I, and this is an N, and this is an E, and this is an R. Liner, linear, liner. Yay? Liner, linear. It needs to look linear. We need independent, which is the 10% rule. We need normality for the residuals. We need equal variability for the residuals, and we need a random selection. Maybe it helps you on test day. I don't know. It's not on my test. Y'all okay with the conditions? I don't think it's important enough for them to put on the AP exam to test it. I think they would rather do other things with that out of the 5 to 7%. But it is homework. So they'll ask a couple of questions about homework conditions. Everybody okay? Soak it up, whatever you need. Use it today, use it tonight, and probably forget about it. Maybe keep that liner in the back of your head somewhere. Random. Okay, look, just watch again. Miss Barrett's class did a fun experiment using paper helicopters. I don't know what a paper helicopter looks like. After making 70 helicopters using the same template, students randomly assigned 14 of them for each of the 5 drop heights. So they went to a drop height and dropped 14 of them. Drop 14 of them, drop 14 of them. And they say they looked at how long they stayed in the air. This is what the dot plot looked like. It looks weird because we're not used to seeing a non-scatter plot look non-really scattered, but this is the height of 150. Here's the height of the 200. Here's the height of the 250. Sorry, not the height, the distance, how long it was in the air. Okay, it looks linear. There's a scatter plot of the residuals. That looks equidistant about the line. There's the normal probability or the normal plot of the residuals. So we have a random, the data looks linear. Independent. 70 is less than 10% of infinity, because you can drop it as many times as you want. I-N, L-I-N, N, 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 N. Normal. The residual plot looks normal. L-I-N-E, equidistance for the residuals. That looks good. And we got a random sample. L-I-N-E or L-I-N, L-I-N-E-R, L-I-N-E-R. Sorry, bad spelling. All good enough? Again, just tonight, don't worry about it. Click. Oh, don't overreact to minor issues about graphs. Don't overreact, just like we didn't overreact with the data about looking somewhat normal. Okay, click. A estimates alpha, B estimates beta, S estimates sigma. You already know the bottom one. A estimates alpha, that's not the significance level, that's the y-intercept. B is the slope, B and beta. You don't worry, you don't care. You don't care about the formula. Now we're starting into getting into possible questions. I'll tell you guys on Tuesday what to expect on my test. I am shooting at the dark. 95% of it's going to be chi-squared. 95 of the test is going to be chi-squared. So chi-squared, 1, 2, and 3. Computerized printout. This is what you have got to know how to read. This is what AP could ask you. They could give you something like this, right? We talked in chapter 3 about this being a constant, and we got drop height, constant and drop height, and we have coef. Oh, I kind of remember that. And then this number right here is the y-intercept, and this number right here is the slope that you need to know. That's chapters 2 and chapters 12. Chapters 3, and I keep getting that 2 and R3 confused. Chapters 3, unit 2. That you should have known already. This down here, the standard deviation of the residuals. You should know that already. This S squared, you should know that already. Sorry, R squared, you should know that already. And if you take the square root of that, you will get R. R is the coefficient. No, R is the correlation coefficient. R squared is the coefficient of determination. Oh, how am I going to remember all this stuff? That's why we got a month to review. R squared adjusted, we don't ever use for anything, ever. Now, notice a couple more things now you probably do know about. The standard error of the coefficient, that's the standard deviation of the sampling distribution. That's the standard deviation of the sampling distribution. I'll show you in just a second what we need to do with it. Here is the t-score. That is the test statistic. I messed up yesterday and called it the wrong thing a couple of times. That is the test statistic. And then this is the p-value. That's the p-value. And so this p-value comes from the test statistic. So one question, 1 year, the below printout, the below linear regression computerized printout was printed with all this, and then of course it gave you all this information, right? Unfortunately, due to a computer malfunction or a printer malfunction, that number was smudged and we can't read it. What is that number? Basically is what they asked. And so we had this T number right here, and we just had to do TCDF to turn it into the p-value. Kind of okay with all that? Okay, good, good, good. What is the estimate for A? That's the alpha. Well, the estimate is the y-intercept. What is the estimate for beta? Well, that's the slope. What is the estimate for sigma, which is the standard deviation, which comes from this? And what is the estimate of, or give the standard error of the slope? And the standard error of the slope is right down here. They don't care about the y-intercepts for this stuff. I don't think I've ever seen them ask anything about y-intercepts for that. It's always been slopes. Everybody okay? Good? Keep following? Click. Oh, I'm doing so much better. Here's your A, here's your B, there's your S, there's your S sub B, sub B. Yada, da, da, da. There's the, who cares? Now let's talk about confidence intervals for slope. Confidence intervals for slope, which you guys already know the formula, because the formula is the same thing for all confidence intervals. It is the statistic plus or minus the critical value times the standard deviation of the statistic. That's what it is. For this, your statistic is going to be B, not X bar, not P, B, because it's slope. Your critical value is going to be T star, and we put the star there sometimes and sometimes we don't. Now, here's an uh-oh. A lot of students want that, and luckily this happened yesterday because somebody asked me about it, so I'm so glad. They want to put that from here. No. No. This is not the critical value. This is the test statistic. Those are two different values. And at some point, I knew I was supposed to beat that into your heads, and it hasn't come up until now. And I should have done it in Z's. I should have done it in Z's. I sure should have done it in T's, and now I'm doing it now. So let's kind of side note. This has nothing to do with anything other than, I guess it has something to do with everything, right? We have, let's do P hat plus or minus Z square root P1 minus P over N. Those are hats. Yay, y'all kind of remember that. Hopefully it's chapters, that was 8. That was one of the first things we did in inferences. We also had this one for chapter 9. P hat, whoops, sorry, dadgummit, I don't have an eraser. It's not worth it. Square root P1 minus P over N. This found the test statistic. This number and this number are completely different. You turn this one into a p-value. This one you get from 99, 95, 96, 90, whatever level they tell you to get is what this number comes from. Yes? They're completely different. And I think that's why they like to put the star there, to make sure that people know that those are not the same thing. They are definitely related, but this one's called the critical value. This one's called the test statistic. And I can easily see how the heck you guys could get confused on that, because they're the same stupid variables, but they don't mean the same thing. This is for hypotheses testing. This is for confidence intervals. This is for hypotheses testing. It's not for confidence intervals. It's a completely different number. Okay? And then they're going to do the standard error of the slope. It's really all you need to know. The standard error of the slope. Okay? So this is going to come from the computerized printout. This is not going to come from the computerized printout. This is something you're going to have to find by either calculator, table, Desmos, Coach Mayer program, critical value. Think back to Coach Mayer program, those of you that used it, right? proportions are means. You clicked means, and then it said DF is n minus 1 if means, n minus 2 if slopes. So that's what we're getting ready to talk about. Click, click, click. Oh, that's where it was. Sorry. I went click too far. That's one of the big differences. DF, n minus 2. DF, n minus 2, not n minus 1. If you can remember that, that will more than likely get you everything you need to know on the AP test. Every AP question I've seen with slopes or testing had to do with that n minus a 2. Finding the critical value, you had to know that the DF was n minus 2, not n minus 1. Finding the test statistic, let me rephrase that, sorry. Finding the p-value, you had to know the DF was n minus 2. And it's because you're estimating two things. You're estimating the slope and the y-intercept. That's why they want 2. Okay, click, click. Oh, that's what this says. The values of t given in the computer regression output are not the critical values. They're not the critical values for the confidence interval. Okay, when we did chapter 3 many moons ago, October-ish, right, we talked about the price of a F-150 and how much it goes down when the mileage goes up. Oh, I kind of remember that maybe. This was the miles driven and this is the price for the truck. Yay, good, got all that data. I could, you won't, put all this in the L1 and put all this in the L2 and do all my linear regression stuff. And you actually can do the confidence intervals and the test with your stuff in your calculator. They won't make you do that. They're going to give you the computerized print output. Click. There's a picture of the residuals. Doesn't look real great, but it doesn't have any outliers or strong skewness. There's a picture of the data. Looks linear. There's a picture of the residuals. They seem to be equal variability. We have all the conditions are met. Here's a computerized print output. Here's the y-intercept. Here is the slope. Okay? Here's S. Here's R squared. Here's the standard error of that coefficient. That's what you're multiplying it by. Again, we're not using y-intercepts. We're not using y-intercepts. We're not using y-intercepts. Here's the t-score. Negative 5.26, and here's the p-value. We're not talking about that right now because we're talking about confidence intervals. Yes, no, good, maybe. That's what you need to extract from all this stuff. Now we got to figure out what kind of question they're going to ask me. They didn't ask anything. What is it? They want me to do a confidence interval. To do a confidence interval, we're going to take B, negative 0.16292 plus or minus the T critical value, which is not negative 5.26. That's where you got to go. Calculator. And either use Desmos or use your table, Coach Mayer program, or inverse T. And this is where you can, if you do inverse T for 90%, this is the trick. I got to remember all this stuff. If you're going to go inverse T for a 90% confidence interval, you got to do 0.05. 90% leaves 10 left over, which is 5%, 5%. Oh, I kind of remember that. So I got to do 5% with a DF of 14 because there were 16 trucks. So that's the T critical value, negative 1.76 or positive 1.76 because it's plus or minus. If you got Coach Mayer program, right, that's the critical value. We hit enter on the critical value. It's means, and it's 0.9. Enter DF, n minus 1 if means, n minus 2 if slopes. 14, click. There's the t-score, 1.761. Yes?
Is the Coach Mayer program allowed on the AP test?
Don't ask something you won't know the answer to. They do not reset calculators.
Yes.
They do not reset calculators. Fair? I'm not answering that question. It's not allowed. I cannot accept the hope. Just fail to reject it. However, he does love you. And you owe him some Cheez-Its. You're going to really owe him some Cheez-Its when I show you something else that's may or may not be allowed on the AP exam. Three, defining. If you want to interpret anything, like I forgot how to interpret the p-value, assuming ho is true and there's no difference between. If you forget that the correlation this is wrong, I got to fix it. The correlation coefficient is not r squared. Remember my stupid little saying, correlation coefficient is c squared, which is not r squared, and I messed up and put it as r squared. The correlation is 3, that's r. That is the strong, weak, linear. I don't know if it's allowed, probably not, but they don't clear calculators. More. Slope, standard deviation, type 1, type 2. More. I got extras just in case there's something else. Created by Coach Mayer and some student. I'll take that off. I don't want to be accused of that. Okay, that has nothing to do with anything other than our review, which is coming up in a while. It's their fault. This is all going on the internet. I need to cut all that out. If there is ever a 325 secret, of course, you don't have crap right now, so it doesn't matter. I do. Okay, click. Sorry. Apply. Your important part right now is to know what that t-score is and how to find it, because that could easily be a question. But that was a question in chapters 10 and chapters 11. So you got to know how to find the critical value, but you should have known that from chapters 10 and chapters 11. So it's the exact same thing now, except your DF is different. Good. Click. So here's that T critical value. Here is that standard error, which we're going to get from right here. Okay. So this plus or minus this times this is your confidence interval. And you can do the math to finish it, or you don't have to. You can leave it like this and they don't care. Click. This is also talking not about this, but about AP in general, or AP stats. When you see a list of data, wait a minute before you start typing it all in your calculator, because chances are really, really good you're doing something wrong. They do not want you wasting time punching a bunch of stuff in your calculator. If you are, I'm not saying you're doing it wrong, but there's a whole lot easier way to do it. So AP exam that's coming up, May whatever, there's 2 sections. There's a multiple choice and there's a free response, right? There's 40 multiple choice on the free response. 40, twice what I always give you. There's 6 free responses. More than twice what I give you. You got an hour and a half here and an hour and a half here. This is plenty of time. Nobody ever complains about this, and that's not. There are many students that run out of time on the free response. Just keep that in mind. If you're using a bunch of time to start punching a bunch of stuff, thank you, my friend, bunch of stuff to plug in your calculator, you're doing it wrong. Okay? That's why I tell you guys to shorten up things you can. Spend more time writing it on Ho, and on Ha, say there is not. That's why I try to give you about 13 minutes to do a frappy question, because that's about how long it should take you. Because if you take 6 and you divide it by an hour and a half, you're going to come up with about 15 or 16 minutes. However, number 6 will always take you a lot longer than that. Okay, let's finish this up. Click. It's for Avery. You got an appointment or something coming up. Significance test for slopes. You know the standardized test statistic is equal to the statistic minus the parameter. You already know all this stuff. It's your job to turn it into variables if you have to. Your standardized test statistic for this is T, right? It is T. Your statistic is B. Your parameter is beta, or whatever your Ho is. Your standard deviation of the statistic is that. Whoops, that's a B. Okay. So I need to talk about the Ho and the Ha for this. Ho. This could easily be a question. Beta equals not B, because B is from a sample. Ho's are always from the population. Ho's always have the equals. More times than not, that's going to be 0. So again, let's think for this talk for just a little bit. Hopefully we have an aha, right? Beta is the slope. If beta is 0, then that means what about the slope? It's 0. It's like straight across. That means what type of relationship? None. We're going to try to prove there's a positive relationship or a negative relationship or a relationship. Y'all follow what I'm saying? So if there's a positive relationship, this beta is going to be greater than 0 because we're going to have a positive slope. If there's a negative relationship, it's going to be less than 0. And if we're trying to find a relationship, we're going to do not equal to. Yes, no, maybe? So let me tell you one more thing that I blew yesterday, first class. I'm going to go back. Let me get rid of all this stuff that you can or cannot see. Okay. Whoops. Dadgummit. Cancel. I'm trying to upgrade it, but I don't have money. So here's the T critical value, and there's the P value. That P value has been doubled. That P value is for a 2-sided test. So if we're doing a greater than or less than, then you need to cut that P value in half, because this has been doubled because it's a 2-sided test. Y'all okay? These little bitty things like that are what they're going to test you on. They're not going to take their time to test you on conditions. They're going to ask you, do I reject or fail to reject? What is the p-value? What is the t-score? What is the confidence interval? Construct and interpret. Actually, they won't say construct and interpret. They're just going to say, what is the confidence interval? The conditions have been met, because they're not going to waste your time to test these conditions. Y'all okay with that? So if you can remember, DF is n minus 2, and then take the stuff you know already from chapters 10 and chapters 11. And if you know that that p-value has been doubled, which you kind of have to take from chapters 10 and chapters 11, and you know the DF is n minus 2, which you can't take from chapters 10 and chapters 11, but you can take all the T stuff. That's what's going to get you through this lesson. click, 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 click. Here it is, non-hieroglyphics, right? B in the hypothesized slope. And more times than not, your hypothesized slope is 0. We assume there's no relationship. Oh, that's what we did with chi-squared. Yeah, well, we assume there's no relationship. That's what our assumption has to be. We're trying to prove there's a positive relationship, negative relationship, or there is a relationship. There's your n minus a 2. Here we have infants who cry easily, yada, 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 yada. Here's their cry count and their IQ. They're trying to show a relationship. I don't know. I got all that data. You start punching this stuff in your calculator and you're probably doing something wrong. And sure enough, here's the computerized print output. And here's the least squares regression line. Here's the residual plot. And there's the residual graph. All that stuff is what they're used to giving you. Do these data provide convincing evidence of a positive linear relationship? I could see them asking for write the hypotheses for this. I could see them asking that question. Or multiple choice. Which of the following is the hypotheses for this? Okay? Your hypotheses for this, you have a hoe. Beta equals 0. Ha. Beta is greater than 0. Because we're trying to prove there's a positive relationship. And then don't forget to define B. You have to define variables. You had to define P. You had to define mu. We didn't have to define anything in chi-squared because we wrote it in context. Where B is the true slope of the regression line between cry count and IQ. Okay with all that stuff? Maybe, maybe not. I don't know. It won't be on my test. I don't think. If it is, I'll tell you Tuesday for sure. Tuesday, Monday, Monday, Monday. One thing you need to remember, my p-value is not 0.004. My p-value is 0.002. Not that it matters because you're going to reject both. But it does matter if they ask you for the p-value, because if they ask you for the p-value and you put 0.004, you're going to get it wrong because it's a one-sided test. Yes, no, maybe? Whew. I got to give everybody in B Day a big old hug. I did a crappy job with them. No, because of p-value for two-sided test, there's evidence that it were one-sided test. Boom, 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 boom. Because the p-value is low, we got to reject. If you reject, there is enough evidence to say there's a positive relationship between. Positive linear relationship is probably what I need to say. I'm going to say that's what, yeah, positive linear relationship. Yes, no, somewhat, maybe. Boom, boom. Your calculator will do these if you have to. You can put your X's in L1 and put your Y's in L2, and then you can do a lin reg T test. And when you do the lin reg T test, which we actually did in chapter 2 so that we could get this S value, if you guys, oh man, if you can remember that, you got a good memory. There's the T-score, there's the P-value, there's the DF, there's the A value, there's the B value, there's the S value, and if you go down further, it gives you some other stuff. Yes? No Z's. Anytime we have means or numerical data, it's T's. Okay, I think you remember saying that one time. Now it's starting to make sense. Any proportions are your Z's, any means are your T's. This is linear regression. It's actually numerical data. It's bivariate numerical data, and I think that's why they threw it in here. Because we have bivariate categorical data. Now we're having bivariate numerical data. Click. If I did a decent job, you can be able to check the conditions. You won't have to on the test. Chances are really good you won't have to on the AP test. You'll have a couple of homework questions. Hopefully you can interpret the values of B sub 0, B sub 1, sigma, S sub E sub B sub 1. Construct and interpret a confidence interval for the slope. Perform a significance test.